I'm talking about a topic that's near and dear to both Intel and my heart. Large-scale, high-scale, extreme-scale computing, or we call it exascale. It's also I'm impressed that there are so many people eager to program these machines. I only work on the design of these machines, and I have great respect for people willing to program them. I think the only thing harder than writing a parallel program is debugging a parallel program. So I don't know if any of you are into the debugging part. Now I have more time than I expected. As we were driving here in the limousine from the airport, one of my fellow travelers said that when people talked about computers, they often use these acronyms and buzzwords he doesn't understand. And so if I use a buzzword or an acronym you don't understand, please take the extra time we have to stop me and make me explain it, what it is. And this way maybe it could be more interactive than a keynote normally is. So what's exascale? It sounds simple actually. You just take a Xeon Phi CPU. Now you may not know what a Xeon Phi CPU is, but it's kind of like a GPU or an NVIDIA card or a graphics chip. And Intel is trying to make it a little more programmable, somewhere between a graphics chip and a regular CPU. So you take, but one thing they have in common is that there are lots and lots of floating point multipliers and adders and cores on these chips. So you have lots of these flops. You add some memory and some I/O. You put multiple of them on a card. You stick many of these cards in a cabinet. You add some networking, and you fill the warehouse with cabinets, and you have a supercomputer. So how hard can it be? So then, when we look at exascale, then I kind of realize that exa is a very big number. This is from Wikipedia. In fact, it's so big it was only recently discovered in 1976. And when they discovered exa, they also discovered zeta and iota, so which are the numbers to follow. So the exa, of course, comes from 6 in Greek, and it's because it's 1,000 to the 6th power. So that's 10 to the 18th, of course. So to appreciate how big this is, 1 exasecond is about 32 billion years. 1 exameter is about 100 light years. Now, in terms of the age of the universe, how many exaseconds do you think the universe has existed so far? It's about 0.43 exasecond the universe has lasted so far. And 1.6 exameter is the size of the Omega Centauri, one of the largest known globular clusters with about a million stars, which I have a picture of there. So you sort of realize, wow, imagine a computer that executes 1 exa operations or floating point operations per second. Then that is pretty mind-boggling. So you might think that instead of being real simple, maybe it's like hopelessly complicated. How could we ever make such a machine? So you look back on the history a little bit of supercomputer growth. And it turns out that since Cray won in 1976, supercomputer performance has grown roughly by a factor of 1,000 every 11 years. So that's almost doubling in performance every year. That's actually twice the rate at which general purpose computers have grown in performance. So how is that possible? One thing, it's measured by the LINPACK benchmark, which is kind of cheating on the benchmark. It's a very simple application. Also, historically, there's been really no limit on the system size. That is, you could always add more nodes. Of course, in your laptop or your desktop, that wasn't always the option. Actually, the LINPACK performance pretty much grows linearly with the transistor count. You add more floating point units, and you get more LINPACK performance. It wasn't always this way. Like 20 years ago, LINPACK performance on the highest rated computers with LINPACK performance was, they published a list every couple of months or so, and we were eagerly waiting to see where we fit on the list when I worked at Digital or Compaq or Intel. But then eventually that benchmark was cracked, and now it's basically for the at least by the large scale version where you can change your code, you can pretty much make the performance linear or match the peak floating point performance of your system. Recently I saw there's a proposal to replace LinPack as the supercomputer metric with a conjugate gradient application, which I think would be a major improvement. And it's a little hazardous to have a benchmark that actually grows linearly with transistor count because you may lead you to design the wrong kind of systems. Now, one thing that happens now is that the Exascale, and this is basically from the US government, Exascale performance comes with a limit on power. They really want Exascale performance at 20 megawatts. And suddenly, that's a new twist on the history of supercomputers, that there's a power limit. Until now, sort of power has been an issue between your accountant and your power company, and how do you deliver all this power. When you turn these systems on and off, usually you had to tell your local power supplier that you're going to do that. As you draw 20 megawatts from your Edison company, then it makes a big difference. But this time, it may be true that actually that goal may be unachievable, at least in this decade, maybe in ever. But I think it's a reasonable goal to strive towards, and it may even be reasonable to work out sort of the unit of supercomputer power delivery to be at 20 megawatts, so that your performance may really be how much you fit in 20 megawatts, or it may be limited by reliability or other factors. But I think it's a reasonable goal. Where do you think we are now? How many gigaflops do you think you get per watt today? And so a Xeon Phi chip has about a teraflop, and it's probably about 150 watts. If you don't count anything outside the chip. So it's on the order of 7 or so. Now 7 gigaflops per watt. And that's actually quite high. If you also include the power distribution, the cabinets, the power converters, the memory system, the I/O, the network, things only go downhill from there. So it's probably more likely to be 3 or 4 gigaflops per watt when you include all the overhead. So getting from 3 or 4 to 50 in a few years is not so simple. So let's actually look at some points along the way. This is a picture of a system of the chip that I've been involved with, the Xeon Phi K and C. I always trip over these. We have sort of code names, and they call Knight's Corner is the name of that chip. So I work on that chip a couple of generations after this one, and I think marketing has a number for this. It's called X100, I think now. Do anyone know? No, it doesn't really matter. But so the Knight's Corner chip is the one that's shipping, and that's the one that's being used in the Tech Computing Center at the University of Texas in Austin, which delivers about 6 petaflops with 6,400 such nodes. The largest system that I know about is the one in China, the Tianhe 2 that you referred to, and I believe that has about 50,000 KNC chips and gets to about 50 petaflops peak performance. So actually this chip consists of roughly 16 flops per cycle. The core frequency is 1 gigahertz. The cores per die is about 60. And in that particular system, it's 6,400 nodes. If you sort of estimate what things will be like going forward, you can imagine the flops per core go to 32. The frequency of each core, we ought to do better than 1 gigahertz. And the core count, we should go to 100 from 60. And the sockets, let's say we go to 100,000 sockets. And if you convert from binary to decimal, which is not an exact science, but if you get 10 squared, you get 10 to the 9, 10 to the squared, and you add up the exponents, and sure enough, you get 18. So it's actually plausible to get an exascale computer in this decade. But not at, I think not at 20 megawatts, but maybe not very far off. For a company like Intel that makes money from selling computers to everybody and building expensive factories and then stamping out the chips by multiple millions, the trick to being able to afford a supercomputer, although now I think looking at this large audience, I'm thinking maybe there is a market for a supercomputer. So as long as each of you buy one and get your mother to buy one, your cousin to buy one, it will hopefully add up. So the trick for Intel, of course, is to use the same chip everywhere. And so in the upper left corner, you see the CPU chip attached to a router and to a giant network. Below there, you can imagine a fully connected system where there's a single network connection between each of the nodes without the router. You know, this is already such a system, say with 8 nodes or 16 nodes. It's already more compute power than most countries have today. These are good-sized systems. Then, of course, you could also have a workstation where you just have one CPU chip, lots of memory attached to that CPU chip, and you can imagine that in a doctor's office, an architect, or as your home computer. And so what do each of these chips look like? Well, if you're going to design a chip with many billions of transistors, they better look mostly alike. And so you stamp out, you organize these cores in a mesh or in an array of tiles, and you line them up with some memory controllers and network interfaces along the edges. Each of the tiles may look something like this. You have a processor inner core, you have a vector unit, you have a core cache, and maybe you have a large distributed cache, and you have some connections into the network. And in terms of designing the chip, all you really care about is that this tile is rectangular. If it isn't rectangular, you make it rectangular with white space until it fits in the grid, and it's your computer. So far this looks pretty simple. We sort of covered the first part of this, but there are some challenges. I stole this slide from somebody, and on the slide when I stole it, it said, you know and I know and the American people know there are some challenges to Exascale. And so here are the 4 major challenges I think that where we need some breakthroughs. And it isn't just predictable that this will happen. One is dealing with the power. And the power has many aspects. I'll deal with a couple of them. There is memory access, and actually I kind of picked memory access as the focus for this talk, mainly because I've been working mostly on that problem personally. Then there's reliability issues, and then there is, of course, how do you program this? How do you actually exploit all this parallelism and apply them to an interesting physical problem to be solved? But let's talk about memory. So I found this quote from, it's actually several people, but the one I recognize is John von Neumann. And this is from 1946, where he says, we are therefore forced to recognize the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. And that was 60-some years ago, and it's an unbelievable insight. We're sort of discovering this in the computer design business. We're discovering this every few weeks, and we're sort of faced with it every process generation that this problem gets a little bit harder. But this group of people actually predicted this 60 years ago, when the problem was similar, but also very, very different. So actually another somewhat famous paper was published by Wulf and McGee in 1994, which they called the paper Implications of the Obvious. And it's still sort of obvious, but that the time to access memory is sort of a simple formula, and you have caches, and you have cache hits, and you have cache misses, and sort of the sum of the time to access each of them multiplied by the probability of ending up accessing that part. So you have compulsory, you have capacity, you have conflict misses, you have cache, of course, lots of architects working on cache design, and clever or brute force cache design helps with capacity and conflict misses. But if every fifth instruction reads memory, when your time to average time exceeds 5 instruction window, that may be the end of computer architecture, which may not seem serious to you, but to computer architects that's a big problem. And compulsory misses alone, especially in high performance computing, may get us to this limit. Now this is a major reason why we're going to CMP. Paul mentioned that companies like Intel have stopped making faster single-stream computers. We're making more computers, but as your latency to memory grows, it's very hard to cover that latency with a single stream, with a single instruction stream. With multiple cores, you can now expose more memory references, and you can turn your memory latency problem into a memory bandwidth problem, which reduces a hard problem to an unsolvable problem. And you may not think that's much progress, but it is the path we're on. This may signal the end of computer architecture. That is, so suppose you believe all of this, that every fifth instruction accesses memory. Suppose that's fundamental, and actually it's not off by very much. I think it will vary from application and scenario, but it's roughly true. And if you can't do anything about memory, the time to access memory, that's basically dictates how fast your program runs. So if you try to execute more instructions at the same time, you end up still waiting for that memory and that dictates how fast your program runs. So there isn't really, you can add branch predictors or more floating point units, but it doesn't speed up because you're just sitting there. If that time, you've now taken everything else and made it take 0 time, you're now just waiting those 5 cycles for memory access time for your program to proceed. And so, but of course, computer architects are not that easily stifled, so easily discouraged. We'll see how this has happened. It is very, I think, in my mind, that this is maybe the most crucial aspect most crucial reason for going to chip-level multiprocessing. Because you could actually have made the processors a little faster. Not as fast as they have progressed in the past. In the past, the reason why processors have gotten so much faster is actually the chip-level integration. As we move the components together, from the first machine that I worked on, the first VAX actually, the components are spread among boards, boards in a cabinet across multiple cabinets. So the time to communicate across all of that to execute single instructions was just enormous. It's like a few thousand times longer than the cycle times we're talking about now. And but as we move all of these components together, and actually I think the next slide talks a little bit about this. Yeah, so what makes memory different? Intel is a chip integration company. So here I grabbed a bunch of die photos from various Intel chips, and they go from a very primitive processor with just a portion of the core of the processor on the die. Then we threw the floating point unit into the processor. Then we put caches on there. We put in hyper-threading that you run multiple threads on the same core at the same time. We added the vectorized floating point instructions. And then comes then it's logical to actually put multiple cores, put a vector unit, a memory interface. I don't know how the printer got on there. The network, the PCI Express. So there's like this is such a success story. The word Intel actually stands for integrated electronics, and that is the secret to Intel having a good business all these years. So why not just toss the memory onto it and solve the whole problem? Well, with memory, it's a little different. As John Neumann said, there's no memory is ever enough. If you could actually fit it on, then people will immediately ask for something that doesn't fit. They will double the requirement. The reason why we want high-performance computers is we want to process more data, and we want that data at our fingertips as we move along. And so the best solution to that, of course, is caches. I mean, caches In this gift that just kept on giving. The first machine with cache that I'm aware of was an IBM machine, 36085, which came out in 1969. That was 25 years after von Neumann decided that this was obviously needed. And it had a 16K byte. They call it buffer, but it's really a cache. The first level cache nowadays is typically 32 kilobytes, so it's only twice as big as this one. But the next one is the memory goes up to 4 megabytes. Now, if memory had stayed at 4 megabytes, we could easily have integrated. It would be on die now, but it's off by, while the cache has grown by a factor of 2, the memory has grown by a factor of a couple of thousand. It's now like 8 gigabytes or 16 gigabytes of memory with a CPU chip. It was write through, write allocate, and if you're into cache design, you'll know what all of this means. Unified means it's both instructions and data. It had 64-byte blocks. That seems to be an invariant. The most computers designed nowadays still have 64-byte blocks, and pretty much everything in between had that as well. The 36085 actually came out roughly at the same time as IBM's maybe most famous 360 machine, which was the 36091, which was the first serious computer to do out-of-order processing. And it was actually a very elegant design. Some of the lasting features from it is something called Tomasulo algorithm, which is how you do register renaming to make out-of-order processors work today. So those same algorithms are actually still in play in Intel chips now and as in IBM chips. So we're making caches better, and actually it is a very important part of computer architecture. I think it's maybe the most successful computer architecture idea we have come up with. We're making caches bigger, multiple levels of caches, more associative, which gives you better hit rate. We have better allocation algorithms to make multiple threads coexist in the cache for better sharing. We're reducing latency, we're adding ECC for reliability, we add new functionality to the cache all the time. And chips to some extent have gone from mostly cores to a little bit of cache to now it's mostly cache with a little bit of cores. And it's probably a recent trade-off. There's still some fundamental limits to how well cache can work, especially in HPC. So what do you do once you're faced with this problem, or if you're a computer architect and you're faced with unemployment? So we want to push back this wall. Now, the best idea that I know about, which we are pursuing, and I think is very interesting, is to stack memory chips on top of each other. So if you look at this picture to the right, you imagine a multi-chip package with the green package substrate. You have the CPU chip lying there in the middle, and on each side you have a stack with a little logic chip and memory stacked on top. And then through silicon vias means that you actually drill through holes through the chips. You fill it with some conductive material, and you communicate. You actually get thousands of connections between these chips, and you get very short wires. And the best part is that DIMMs, is this part here. You power a single page. That in a DIMM, you have multiple DRAM chips lined up on the DIMM. You send out the same address to everybody. Inside each chip, that address selects a page inside the chip. It reads out actually thousands of bits from each DRAM, and then it funnels out a handful of bits which then gets collected up and sent back to the processor chip. That's an unbelievable waste of power. It's also very slowly. It's high power, long latency, but what's good about it? It's high capacity, and it's very convenient if you're a DRAM manufacturer. So actually, it's a good design. But before power became an issue, it was especially good. Now it does sort of fall behind. So with a stacked memory design, you only power the chip that you're interested in, only power a single page. Each page is like an array of bits, and it's typically like 4,000 to 16,000 bits wide. And you really, for a page, for a cache line, you only want 512 bits, and you can easily get them from a single page, except that on DIMMs you get them from 9 or 18 DRAMs, and you power 9 or 18 times 2,000 or 4,000 bits to get them. Yeah, so we can reduce the need. We also try to reduce the need for memory bandwidth. You can have bigger, better caches. You can have data compression on the memory connection lines. You can have sub-block transfers. That's a little interesting. That the 64-byte blocks have become the standard for block size in memory systems. But how is that arrived at? It may well be, nobody really knows, at least I don't know. But once we pick that size, it's very hard to change because I/O and disks and everything line up around the same size, so you can't really change it lightly. But it may be that, of course, a cache line is sort of based on temporal locality and spatial locality. In addition to this 1 byte, how many other adjacent bytes do I also want? And 64 bytes may actually be an average. That the typical one may be there's a lot of 8-byte accesses, a lot of 4-byte accesses, and maybe a lot of 1,000-byte accesses. And if you average it all together, you get 64-byte accesses. But nobody really wants exactly 64-byte accesses that we settled on. So it's reasonable to look to support other cache lines, other units of transfers, and maybe have 8-byte sub-blocks that you could actually cache and just do the transfer. And now you could increase your memory bandwidth by a factor of 8 in many applications. Active memory operation means you actually do the work in the memory itself. You don't really bother transferring the data to the CPU. So you get this new kind of memory hierarchy. With the stacked memories, you get high bandwidth, low power, actually like maybe 1/3 of the power that you would with DIMMs, but you get low capacity because it's actually limited how many DRAMs you can stack on top of each other before you have a heat dissipation problem or you have a manufacturing or reliability problem. Traditional DIMMs, you get low bandwidth, you get high power. Those are both bad, but high capacity is very good. So for lots of applications, high memory capacity is very valuable. You can now also start thinking about third-level memory, and there's lots of new memory technologies that are being researched and are starting to show up. When they typically have low cost per bit, and most of them, I think maybe all of them, have this characteristic that they're non-volatile. So you're getting that whether you want it or not. I'm actually not sure whether how important it is. But you can imagine that it's nice to be able to turn your computer off, and when you turn it back on, all your memory data is still there, and it responds very quickly. But of course, there's 3 levels of memory, and actually, I think in supercomputers, you may well have a mixture of these 3 levels. So this is a little bit of a challenge for software to control this and take advantage of it. You now end up with fast malloc where you allocate memory in your stacked memory chips. You have malloc for your DRAMs or your DIMMs, and you have slow but persistent malloc for your third level of memory. When you think about how you program, do you know where to put your data? It's, in some sense, data that fits in your cache, you may not really need it in your fast memory because it sits in your cache all the time anyways. And even though especially if you use it all the time, but the data that you need quite often but not all the time, you may want to put it in your stacked memory. So some solutions, you could use your near memory as cache. And now you're talking about maybe gigabytes of cache. Do you think that's a good solution? Do you ever think of what fits in your cache? Is that like when you tune your program, do you tune for your cache size? Like computer architects try to model cache behavior. It's very hard to model behavior of gigabytes or caches because we can't model problem sizes large enough to actually challenge such a cache. So the things we modeled, trivially fits in a gigabyte of cache. And so you had to build it in order to see how it works. And once you build it, you can't really experiment. It's harder at least to experiment with it. So So we're kind of flying blind in terms of gigantic caches. So it's not obvious to me that software management, like the top one, isn't a better solution than the bottom one that says use it as a cache. But someday whole memory will be fast, large, low power, and maybe non-volatile if anyone cares about that. So now that we shrink circuits and we add more cabinets, what will happen to reliability? So if you have 100,000 sockets, 10 million cores, 40 million threads, what could possibly go wrong? So it turns out, I think for some of the hard ones, we have good solutions for like memory and the network. And I was thinking, why do we have good solutions there? I think it's because they're very regular structures, and we've actually learned to live with errors. We've had memory errors for quite a long time. That is, memory manufacturers have made DRAMs so dense and so fragile that neutron particles are quite likely to wipe out a bit every so often. I actually think it's remarkable that we buy laptops without parity checking on memory. That seems absurd. For like only $10 more, you don't have to deal with your blue screens and stuff. But we save the $10 and curse Microsoft when we get memory errors. But anyway, so for memory memory chips, ECC works very well, and we have bigger ECC, so we can cover more bits, and it works well. Networks also work well. The reason why we're actually quite used to deal with errors in network, because we're pushing up the frequency right to the edge where you routinely have errors. And we learn to live with it by having linked level retries. So when we get an error, we just retransmit the same package, and chances are the next time it just goes through. And so that's sort of routine, and it's acceptable. It doesn't affect the program, and it's invisible to the application. Now the cores are more of a challenge because they're very irregular, and people want them to be low power and fast, and so if we add a lot of error checking to it, they become high power and slow, and the trade-off is much more complicated than it is for memory and network. Now, as we go forward in checkpointing, my understanding is that it's sort of nice in theory, it's hard in practice, and that whether you do it at the application level, the operating system level, at the hardware level is especially difficult, I think. You could also have micro-level retry. That's kind of like transactional memory, where you can sort of execute for a while. If you had no error, you commit the whole state at the end. If you had an error, you back up to the beginning of that transaction, and you can try again. I think it's quite intriguing. I know at University of Illinois, I think Professor Torellas does a lot of work on bulk processing, which is, I think he does it sort of along the lines of memory ordering and actually now I can't think of the word, but basically make it easier to make parallel programs more predictable. But you could also use it for error recovery if we had it. So that sort of leaves detection as the hard part. And you could have hardware checkers, you could have self-checking software, you could have redundancy in the hardware. One of the ideas that has been bandied about for a long time is modular redundancy, which where you do modulo 3 arithmetic, and you can use that to recover. You do the modulo 3 arithmetic in parallel with the operation. You know why that works? It's because it works for the same reason as in order to decide to check if your number is divisible by 3. You can check it, see if the checksum is if the sum of the digit is divisible by 3. That's equivalent, and that's the same in binary. If you do that 4 is equal to 1 modulo 3, and you can use modular arithmetic. Think about that if you have time. One thing I'm interested in is in chaos theory, there is this new new idea of robust, understanding robust systems or developing robust systems. I'm wondering if that can be applicable to systems of the scale that we're talking about here. So power, how do we study climate change without causing global warming? I think that's a serious issue. We talked a little bit about it before, that the government wants all of this to happen at 20 megawatts, which would be great. So miniaturization and chip-level integration saves a lot of power. It also creates a local power problem or cooling problem. It limits physical packaging options, e.g. memory, and makes memory access and network access harder. Clock gating, which says when you don't do something, at least turn off the clocks. With CMOS, that actually saves a lot of power, but it saves the dynamic or active power, but it still leaves you with leakage power, which is roughly a quarter of the total power. Power gating is where you actually turn off the whole function that you're not using. Is more effective, but actually now you consume power to save power, which is assuming that you bought this computer because you wanted to use it. It's sort of annoying to have these power gates sit there consuming power and never really turn off. Voltage frequency scaling, that's sort of how, before most of you were born, actually MOS gates, you always used 5 volt to power them, and the way, and we basically scale power downwards, and now it's less than 1 volt, and since the dynamic power is basically a factor of 2 or maybe 3, it's the voltage supply. Voltage to the power of 3 determines the dynamic power, and so that's a big deal. But now the voltage is getting so low that is approaching the threshold voltage for transistor, and basically what causes transistors to switch is the difference between the voltage and the threshold voltage. So when the minimum voltage crosses over the maximum voltage, it doesn't work anymore. So we're getting very close to that, but it still is an area where people are working hard to extend the range of voltage frequency scaling. But it's obvious to me that we need fresh ideas to get Exascale to work at 20 megawatts. Now, so Intel gets a lot of credit for Moore's law. Gordon Moore was one of the founders of Intel. But the one who formulated this was actually an engineer at IBM, Robert Dennard. He wrote this paper, this was sort of the seminal paper on process scaling. And so basically, if you scale everythh by the same factor, actually the industry has decided that the factor to scale by is the square root of 2, which is roughly 1.4, or the inverse is 0.7. And so if you scale the device dimensions by that factor, the doping concentration, the voltage by the factor, current, capacitance, delay, and some of these are inputs, some others are consequences. The delay is actually increasing or reduced by the scaling factor. And the power dissipation is reduced by the scaling factor squared. And if you do all of this, and you will get twice as many transistors in the same area at the same power each time you get as the process moves forward, which is sort of a remarkable thing. So computer architects have had this ability to work with a material that gets twice as good in just about every dimension every 2 years. And that, imagine if car manufacturers or car designers could do that. Then they wouldn't be stuck just adding cup holders each time, right? But the danger for computer architects is that if this process doesn't continue, then we will be reduced to cup holders. The one problem, this is not scaling anymore, the voltage. And so if you stop scaling that, you don't get this power advantage. So the voltage actually ends up scaling with. The dimensions actually, at least for the foreseeable future, will continue to scale. So you will get twice as many transistors in the same space, but it will be at a higher power level. And so So that seems in general to be what's attractive for customers. Consumers would like more transistors and so that's another reason why you go to more cores, because one way that you increase the speed of processors in the past was not only increasing instructions per cycle, but also increasing the frequency. And the frequency is actually proportional to the voltage. The frequency is roughly proportional to the voltage, but as you increase the frequency, you also increase the power. And without lowering the voltage, which Dennard does, you can't afford to increase the frequency. This is actually Intel's roadmap, and like this would be the exascale generation, and you get 256 billion transistors on a die, and of course it gets harder and harder. It's interesting. I always used to wonder, if we have such a roadmap for how to get there, why don't we just get there in one jump? But each step along the way, they don't really know how to solve the problems in the next few steps. So each step really has like 2 years worth of research by hundreds, maybe thousands of physicists and chemists and others to make it work. So the width of the transistor in 90 nanometer is 50 millimeter gate length, and 50 nanometer gate length, and the virus has 100 nanometer gate length. And if you remember from the slide that had the 4 unsolvable problems, I left the last unsolvable problem to you, the one that says, how do you program these things? And I think that's your assignment for the end of the course. and that's it. I took more time, but you gave me more time. So.